NASA is not returning to the moon because of the moon itself. The Artemis program is not a sentimental journey back to where humanity once left its footprints. It is a calculated move against the most unforgiving force in space, travel the gravity of Earth. And the answer may already exist in craters that have not seen sunlight in billions of years, hidden in permanent darkness, waiting to be used. Every launch from Earth was an act of war against a single, unyielding law of physics. The law was codified in the Tsiolkovsky Rocket Equation, a deceptively simple formula that governed the movement of mass through space. It was not a guideline. It was a tyrant. The equation dictated that, to achieve a change in velocity, a rocket must expel mass, and the mass of that propellant would dwarf the mass of everything else to go faster. You needed more fuel, but that fuel had mass, which meant you needed even more fuel just to lift it. This recursive, brutal logic kept humanity chained to its home world. Escaping Earth's gravitational field was the most expensive part of any journey. Over 90% of the mass sitting on a launch pad was nothing more than the energy needed to begin. It was an appalling rate of exchange, a cosmic tax of breathtaking scale. For decades, engineers fought this tyranny with brute force. They built larger engines and lighter materials, chipping away at the margins of the equation, but never breaking its fundamental hold. The Apollo missions were the grandest, most glorious defiance of this rule. They were a surge of national will, made manifest in controlled explosions, hurling small capsules towards the moon on pillars of fire. Yet for all their spectacle, they were logistically unsustainable. They were the equivalent of building an aircraft carrier to deliver a single letter across an ocean. The missions brought back rocks and photographs, but left behind no infrastructure, no permanent foothold, no way to make the next trip easier. The tyrant always won in the end. Once the political will faded, the sheer economic absurdity of the Apollo model became undeniable, and the journey stopped. The long silence that followed was not a failure of imagination. It was a period of cold, hard calculation. Jennifer Cole spent her days immersed in that new math. Her desk was a constellation of screens displaying orbital mechanics, resource distribution models, and energy consumption projections. She was not designing a mission. She was designing a system. The old paradigm treated the moon as the destination. Her work treated it as the solution. The Artemis program was born from this paradigm shift. Its architects understood that fighting a war of attrition against Earth's gravity was a losing strategy. You could not win by building a bigger battering ram. You had to find a key to the gate. The focus shifted from the single, heroic launch to the creation of a permanent, self-sustaining logistical chain that began after the most difficult climb was over. The goal of Artemis was not to plant another flag on the moon. It was to build an industrial outpost at the top of the well, a place to refuel and resupply for the real journey outward. The moon was no longer the prize. It was the port. The new strategy depended entirely on a resource that, for most of human history, was believed not to exist. The moon of the Apollo era was a place of magnificent desolation, a world of bonedry rock and sterile dust. This perception of an anhydrous wasteland was a core assumption, and it shaped every calculation. Shipping water from Earth was just as energetically expensive as shipping fuel or anything else. But a series of quiet, persistent robotic explorers began to chip away at that certainty, detecting whispers of something anomalous hidden in the deepest, coldest shadows of the lunar poles. The first hints arrived in the 1990s. The Clementine mission, using a clever radar technique, bounced radio waves into the craters at the South Pole. The returning signals carried a signature that was not quite rock. They were more consistent with something crystalline, something like ice. It was a tantalizing but inconclusive ghost in the data. A few years later, the Lunar Prospector Orbiter provided a much stronger piece of evidence. Its neutron spectrometer measured the energy of particles ejected from the lunar surface by cosmic rays over the polar regions. The instrument detected vast numbers of slow-moving neutrons, a telltale sign that they were colliding with hydrogen atoms, the H in H2O. The data painted a clear picture. The poles of the moon were rich in hydrogen, concentrated in the very places the Clementine radar had found its strange reflections. These locations were unlike anywhere else on the moon, due to the slight tilt of the lunar axis. The floors of certain deep polar craters had not been touched by a single ray of sunlight for over 2 billion years. They were permanently shadowed regions, geological crypts where temperatures plummeted to a scant few dozen degrees above absolute zero. These were perfect cold traps. Any water molecule from a cometary impact or solar wind interaction that happened to fall into one of these craters would become instantly frozen, unable to gain the energy needed to escape back into space. Over eons. This process had sequestered an immense quantity of water ice, mixing it in with the lunar regolith. The final, irrefutable proof came with a bang in 2009. The Lunar Crater Observation and Sensing Satellite, or LCROSS, performed a dramatic experiment. It guided the spent upper stage of its carrier rocket on a collision course with the Cabeus crater, slamming it into the frozen darkness at over 9,000 kilometers per hour. A second. Shepherding spacecraft flew directly through the enormous plume of debris that was blasted into the sunlight, analyzing its composition second by second. Jennifer Cole had watched the live spectral readings from that fly-through. She remembered seeing the absorption lines for water vapor appear on the screen, sharp and undeniable. It was the moment an anomaly became a resource. The discovery fundamentally rewrote the equation for space exploration. This was not merely a source of drinking water for future astronauts. It was a strategic reserve of propellant. Through the process of electrolysis, water could be split into its constituent parts, liquid oxygen and liquid hydrogen. This combination was the most potent chemical rocket fuel available, the same fuel that powered the space shuttle's main engines and the upper stages of the most powerful rockets ever built. The coal traps were not just craters. They were fuel depots. Humanity now had a way to source the propellant it needed, not from the bottom of Earth's deep gravity well, but from a shallow one, a mere 1/6 as strong. The Tyrant had a weakness, and if it works, the moon stops being a destination and becomes a fuel station for Mars. The discovery of water was the strategic breakthrough, but the war for the solar system would be won by logistics. That war was being fought not on a battlefield, but on the high-fidelity digital displays of Jennifer Cole. His universe was a meticulously rendered simulation of the Shackleton crater rim, built from petabytes of topographical data supplied by the Lunar Reconnaissance Orbiter's laser altimeter. Every boulder, every slope, every shadow was a known variable in his complex equations. Kenji's work was the unglamorous bridge between theory and reality. Jennifer Cole and her team had defined the grand architecture of the Artemis program. He was the one designing the plumbing. His focus was on the immense engineering problem of turning a frozen, inert resource into a usable commodity. On his screen, a virtual rover, squat and heavily shielded, crawled from the sunlit edge of the crater down into the permanent, cryogenic darkness of its interior. The environment here was more hostile than open space. Temperatures that made conventional steel as brittle as glass, and a darkness so absolute it had persisted since the solar system's youth. The challenge was threefold. First, the extraction. Kenji's simulated rovers couldn't just scoop the regolith. The water ice was a fine frost mixed with abrasive, razor-sharp dust. The machines needed heated augers and sealed conveyor systems to drill into the lunar permafrost and transport it without losing the precious volatiles to sublimation in the vacuum. Second, the power. Solar arrays were useless in the shadows. The entire mining operation had to be powered either by radioisotope thermoelectric generators or by a beam of concentrated energy relayed from a solar farm perched on the crater's rim, a man-made sun for the machines toiling in the dark. Third, And most complex was the refinement. In his simulation, the ice-rich regolith was ferried to a processing plant. Here, it was heated in a sealed container, baking out the water vapor, which was then captured and cryo-cooled into liquid. A portion of that water would then be fed into an electrolysis unit, a machine that zapped it with electricity to split it into pure hydrogen and oxygen. These two elements, once chilled to their liquid states, were the most powerful chemical propellant known. His models tracked every watt of energy, every gram of mass, every second of processing time. He would run the simulation for 1,000 hours, watch his virtual outpost fail in 100 different ways: a joint freezing, a power conduit failing, a drill bit shattering against a buried rockend. Then he would adjust the variables and run it again. This was the tedious, essential work. It was like laying the foundations for a city nobody lives in yet. A painstaking process of preparing the ground for a future that still existed only in blueprints. What he was designing was the first orbital gas station, a place where spacecraft could top up their tanks before venturing out. The first kilometer of the interplanetary highway was being paved not with asphalt, but with code. This outpost on the moon was not the destination. It was the harbor being constructed before the great fleet set sail from Earth. The final piece of the puzzle clicked into place, not on a launch pad at Cape Canaveral, but in the mission architecture diagrams that Jennifer Cole reviewed daily. The success of the entire enterprise was measured by how it fundamentally rewrote the rules for everything that came after. With a functioning industrial base on the moon, the logistics of interplanetary travel were inverted. The tyranny of the Tsiolkovsky equation was not overthrown, but it was cleverly outmaneuvered. A spacecraft built for Mars in this new era would leave Earth feeling strangely light. Its propellant tanks would be barely a quarter full, holding just enough energy for the 3-day transit to the moon and the braking maneuver to enter a stable lunar orbit. This initial launch, while still a spectacle of controlled violence, was no longer the allure-nothing gambit it once was. The vehicle was not burdened with the fuel it needed for its entire journey. It was merely commuting to the real starting line. Docking at the propellant depot in a high lunar orbit was a quiet, almost anticlimactic affair. The depot was not a single, grand station, but a cluster of autonomous, cryo-insulated tanker drones. These drones were the final link in a supply chain that began in the frigid darkness of Shackleton Crater. They were filled with liquid hydrogen and oxygen that had been extracted, refined, and then launched from the lunar surface using electromagnetic catapults or short-burn chemical rockets. Lifting a kilogram of propellant from the moon required 22 times less energy than lifting it from the crushing gravity of Earth. That simple, astounding fact of orbital mechanics was the economic engine driving the entire system. As the Mars-bound vessel connected to a tanker, its tanks were filled to capacity with fuel that had never touched the atmosphere of Earth. This logistical pivot was transformative. Previously, every gram of scientific equipment, every extra day of crew supplies, every redundant life support system for a Mars mission had to be weighed against an enormous mass of propellant. Now, with refueling at the top of the gravity well, that trade-off was radically altered. Payload capacity soared. Missions that were once prohibitively expensive or mass-constrained became feasible. Humanity could now send larger habitats, more robust radiation shielding, and heavier scientific rovers to other worlds. The moon was no longer a celestial body to be visited. It had become an integral part of humanity's deep space infrastructure. It was the industrial harbor for a fleet that had not yet been built, the indispensable port of call for every outbound vessel. The Artemis program was revealed not as a sentimental return to a place of historical triumph, but as the most ambitious civil engineering project in history. It was the deliberate construction of a permanent causeway across the moat of Earth's gravity. The flags and footprints were a relic of a different age, a time when the moon was the destination. Now, It was simply the way. So that cold calculation to defeat gravity led us right back to the moon, but with a new purpose. It turns out the solution was never about building bigger rockets, but about thinking differently about the worlds around us. Those craters, dark for 1 billion years, are poised to become the most illuminated places in human history. The launchpad for a future we are only just beginning to write. The return to the moon is not a repeat of history. It may be the beginning of the next chapter. The moon is not the destination anymore. It's infrastructure. Subscribe to Tech Dissect Official for what comes next. Now that we're on the verge of turning these ancient, untouched craters into industrial zones, what responsibility do we have to preserve the lunar environment? And how do we balance progress with preservation? Let us know your thoughts in the comments below. Thanks for watching, and we'll see you for the next dissection. But as nations and private companies rush to claim this priceless real estate, the next great conflict won't be fought on Earth.